In this video, we'll be talking about moment of inertia. So what is moment of inertia? Well, moment of inertia is MOI, stands for moment of inertia. It's sort of the mass. Sort of the mass in any rotational movement. And just like mass, you can add, so you can sum all the moments of inertia to get the single moment of inertia of a system. And I'm going to have videos explaining that in this video later. Oh, this bullet point. Let's fix this very thick bullet point. Let's make that smaller. But let's teach you how to use this formula sheet. So what does this formula sheet represent? Well, M represents the mass of this hoop. But this could also be a point rotating around some axis. And this M is the mass of the point or the mass of this hoop. Now this hoop doesn't have any volume. So if you have something that does have volume though, you're going to use this formula here. But let's go back to this guy. So this guy rotates sort of in this direction, like so, around this axis, this line right here, the straight line. And the radius is just represented by how far the hoop is away from the axis. Okay, how about for this formula? Well, for this formula, you have a radius of 1. The radius of 1 is the radius of the inner circle. And the radius, so this one right here, the radius of radius 2 is the radius of the outer circle. And this guy has some volume, and it's called a ring or it's called a ring. Now, we have the mass here. You have to divide the mass by 2, and then square both these values, add them together to get your moment of inertia. Now, how about for a solid cylinder? This cylinder is rotating in this direction around this axis. And the length of the cylinder is represented by L. Now, we don't need the length to calculate your moment of inertia for the cylinder. But the reason why it mentions L is because of this guy. So this guy rotates sort of in this direction. Let's go counterclockwise constantly. Let's be consistent with the counterclockwise movement. This sort of rotating cylinder rotates about this axis in the direction of the arrow. And it can be calculated using the mass times radius squared over 4 plus the mass times the length squared. So the length of the cylinder squared divided by 12. And once you add those together, you can get your moment of inertia. How about the axis at the very end? So what if this guy rotates all the way around like so? Well, okay, I'm blocking the formula actually. Let's try to write this lower. But you can calculate this by just multiplying mass times length squared divided by 3. But how about this guy? Well, if you already are understanding how these work and all these pictures, move on to some problems. But if you still need some help, I will keep explaining. So, what about this axis? Well, this axis is usually a thin rod. So this thin rod doesn't actually have any radius. You could sort of think of it as just a one-dimensional line rotating. So you could think of it as something like a stick. You can treat a stick like a one-dimensional line because it's so thin. But for a solid cylinder or a disc, the radius matters. So these two are sort of tied together, but one is a one-dimensional line, as one's a three-dimensional cylinder. And usually you're going to be using this one for very thin objects like sticks or super thin steel rods rotating. So it's honestly not too bad to be able to differentiate them, especially if it doesn't give you a radius. If the problem doesn't give you a radius of your cylinder, then you know to use this guy right here. Okay, well, for these spheres, this one is simply a solid sphere. So this calculates the moment of inertia of a rotating solid sphere. So therefore, it is not hollow. So it's like the inside actually has matter inside of it. This one is for a thin spherical shell. So this is how you calculate the moment of inertia for a empty sphere. So this sphere has nothing inside of it. This sphere has something inside of it. This one has just the circle. Now that we've talked about moment of inertia, let's talk about rotational kinetic energy. So what's the formula for rotational kinetic energy? Formula for rotational kinetic energy is 1/2 moment of inertia, total moment of inertia of a system, times the angular velocity squared, and that's just equal to your RKE, rotational kinetic energy. Now, you can see some parallelisms with this, and honestly, you don't even need to memorize this formula. You can kind of already if you know the linear kinetic energy formula, then you'll know the rotational kinetic energy formula. So, I, as I've said, or moment of inertia sort of represents mass in rotational systems, and angular velocity sort of represents velocity in angular motion. So all you have to do is interchange these between each other of the rotational variables and the linear variables, and boom, you get your rotational kinetic energy formula. And all the units work out as well. In the end, your kinetic energy unit will be joules still. So now that we've talked about rotational kinetic energy, let's move on to some problems. For this problem, we have a system of point particles, important, and each of them weigh 0.3 kilos. And they all lie in the same plane. So all of these rotate around some two-dimensional plane. What is the moment of inertia of the system about the given axis? Well, let me try to help you understand this. If this is the axis of rotation, that means that this particle 40 centimeters away rotates kind of around in a circle like this. This particle 20 centimeters away has a smaller orbit since it's 20 centimeters away, and this circle further away, this point further away, has a 60 centimeter orbit, and it kind of rotates around this axis like so. So if I were to just draw smaller arrows, we would just draw them like this, that kind of represent their orbit. So now we got a understanding of that. What is the moment of inertia of a system about the given axis? So the question's asking, what's the total moment of inertia around this axis? So what can we do here for that? Well, we can add all the moments of inertia together in order to get the total moment of inertia over an axis. But the first thing we need to do is pick an equation. So we need to pick an equation to solve for each individual moment of inertia of all these point particles. So pick a equation. Well, if you picked this equation, then you picked right. And the reason why is because even though this formula states hoops, you can also use them to solve for the moments of inertia of point particles around an axis. So if we were to set up all the points like so, and if I were to name actually these, let's name this point 1, let's name this smaller one, point 1, point 2, and point 3. Let's set up all their equations for their moments of inertias. And once we set up all the formulas for the moments of inertias, mass times radius squared, all we have to do is evaluate these equations to get I. So we have evaluated all these moments of inertias, and I have marked the numbers corresponding to the points I solved them for. So if you look at the work, you might be able to understand what I did here. But I ran out of space for the unit, but the unit for moment of inertia is the same for everything. So the unit of moment of inertia is, well, you have just kilos here, but you squared the meters, so the unit for moment of inertia is kilos meters squared. So maybe just imagine I wrote that all for these numbers. Now that we've solved for all the moments of inertias in this system, we can add them all up together. And when you add them all up together, you get the total moment of inertia of a system. So you get kind of the total mass of the system. Once you've added all these numbers together, each corresponding to the underlined, let's use colors, to the underlined colors, yellow. Once you added them all up together, you should get a total moment of inertia of 0.168 kilogram meters per second. So now that we have the total moment of inertia, let's solve for part B. So for part B, you need to find the rotational kinetic energy. So how do you solve for the rotational kinetic energy? Well, rotational kinetic energy is 1/2 times the moment of inertia times angular velocity squared. So we have our total moment of inertia given by 0.168, but we don't have the angular velocity. We have the angular velocity in revolutions per second, so we need to do some unit conversion. So let's write down 5 revolutions per second, and in doing some unit conversion, you get 2 pi radians is equal to 1 revolution. So doing this, our fractions can cancel out. So we get 5 times 2 pi. If you multiply 5 by 2 pi, you get 10 pi radians per second as our unit. So radians and seconds. So our angular velocity is 10 pi radians per second. Now that we have our total moment of inertia and our radial, oh, why do I keep saying radial? Angular acceleration, we can solve for the kinetic energy. The kinetic energy is equal to 82.9 joules. For this problem, we need to calculate the rotational kinetic energy of Earth. Wow. So this is going to be a lot larger numbers, but the steps will be the same. So pick a formula to solve for the moment of inertia. So in order to solve for rotational kinetic energy, we need our moment of inertia and also our angular velocity. So let's solve for the moment of inertia first. The moment of inertia is solved by this equation right here. Since Earth is a solid sphere, it's not hollow on the inside, no matter what the conspiracy theorists say, we can solve for the moment of inertia by multiplying 2 times the mass of the Earth times the radius of the Earth over 5. So let's set up that equation. Once we have set up this formula, we can evaluate all of this. This is the mass of the Earth, and this is the radius of the Earth in meters and in kilos as these units. Now that we've evaluated the moment of inertia of Earth, we can solve for the rotational kinetic energy once we find the angular velocity. Now, quick side note, if you search up the moment of inertia of Earth, it will not equal this. And that's because Earth is sort of rather than a sphere, it's an ellipsoid, but we're just going to use this approximation for this problem. Well, how do you solve for the angular velocity? Well, you can solve for the angular velocity of the Earth using something we already know, something all of us know, the period of Earth's rotation on its axis. And that period of Earth's rotation is the time it takes for a day. So the period of Earth's rotation can be written like so. And what we can actually do is rearrange this equation so that we get 2 pi over the period of Earth is equal to angular velocity. So what is the period of Earth? Well, we need to change this to seconds. So first thing we need to do, we need to do some unit conversion for hours to seconds. So unit conversion for hours to seconds looks like so. And now that we have the period for Earth's rotation, we can just rewrite this formula. So 2 pi over 86,400 seconds should be equal to our angular velocity. And this right here is your angular velocity of Earth. So now we have the angular velocity, and we have, so let's square this. Now we have the angular velocity, and we also have our moment of inertia. We can set up that equation for part A, for the rotational kinetic energy. Now that I simply substituted all the numbers for our moment of inertia and our angular velocity into the rotational kinetic energy equation, all I have to do is evaluate these numbers. And when you evaluate, you should get 2.57 times 10 to the power of 29 joules for the rotational kinetic energy of Earth. So now that we solved for part A, next step, part B. As you can tell, I'm running out of space, so hopefully I'll have space for this. So let's try to solve this. What is the rotational kinetic energy of Earth in its orbit around the sun? So we're going to have to use a little bit of Google, as you... I don't think anyone memorized the radius of Earth's orbit around the sun. I'm pretty sure it's elliptical, by the way. So we're not going to get a actual the right answer when we're solving this, but we're going to treat it like a circle. So try to solve part B by yourself. Now that you have done it, let's go through this problem. So we need to solve for our moment of inertia. So how do we solve for moment of inertia of the Earth around the sun's orbit? Well, pick a formula first. If you pick the formula to treat Earth like a point, you are correct. So there's technically no, I guess there technically is a formula, but there's technically no formula on this sheet that has a sphere that is rotating around an axis. So we can just treat the Earth like a point. So all we have to do is treat the Earth like a point, and we can set up our moment of inertia equation by multiplying the mass of the Earth times the radius, so times the radius of the sun's rotation. So the radius we're talking about now isn't the radius of the Earth, but it's actually the radius of the Earth around the sun's rotation. So this is what I'm talking about. So this is the sun, this is Earth, this green blob. Maybe I should have drawn it blue since Earth is mostly ocean. But this is the radius of our rotation. So the axis, or the center here, is the sun, and the Earth is rotating around this axis. So let's set up the equation. Once we've set up the equation, all I have to do is evaluate this. Now, let's be a little more clear on this. This is the radius, and this is the mass of the Earth. And we're treating the Earth like a point particle rotating around the sun. So once you've evaluated this formula, you should get, let's change the color back to white, you should get a moment of inertia of 1.34 times 10 to the power of 47. It's a lot greater this time, and imagine I put the unit kilogram meters per second. Let's put that at the top here. So let's box this in because it's important, and let's make a little bit more real estate for us to keep doing this problem. So now we need to find the angular velocity. So the angular velocity, take a guess. How much time does it take to go around the Earth's orbit, or the Earth around the sun? Well, it's just a year, right? That's the definition of a year. So a year is represented by 365 days. So previously we used period. We used the period formula here in order to find angular velocity. So we can actually find the period of rotation again, and what we have to do is do some unit conversion for 365 days to seconds. Well, as we have solved before, the period for a day is, well, 86,400 seconds, so we can use that seconds in this equation here. We cancel out the days unit, and then once you multiply 365 by 86,400, you should get, well, it's a very large number, but let's approximate 3.15 times 10 to the power of 7 seconds as your period. So what we need to do is plug it into this formula. Plug the period into this formula. So if we plug the period into this formula, it should look like 2 pi over 3.15 times 10 to the power of 7 seconds. And now we can solve for the angular velocity. So the angular velocity is quite a small number, but that makes sense since the Earth rotates around the sun relatively slow in comparison to how much distance it's traveling. I'm guessing we're running out of space, so I'll just erase the work for part A. Using this extra space wisely to solve part B, I've set up the equation for the kinetic energy formula for you guys. So this is your moment of inertia, and this is your angular velocity of the Earth around the sun. So now we can calculate the rotational kinetic energy of Earth's orbit around the sun. And once you've evaluated everything here, your rotational kinetic energy is 2.65 times 10 to the power of 33 joules. Give yourself a pat on the back because this was a very annoying and long problem. At least for me. Okay, let's go to the next problem. So this last problem made it very easy for you guys. You deserve it. You've been through a long time, if you have stuck through until the end. But let's calculate the moment of inertia of a long, thin stick weighing at 12 kilos rotating about its center. So take a guess, which formula are you going to use for its moment of inertia? Well, if you chose this one, let's use a better color because yellow doesn't blend in well with white. If you chose this one, you're right. Because of the description, we have a thin stick, therefore we can kind of treat it like a one-dimensional line or a thin rod, as this even describes, weighing in at 12 kilos, rotating about its center. So the axis of rotation is right in the center, which is perfect for this problem. So let's go ahead and set up that equation. I've set up the equation here. This time, I won't run out of space because this problem has like no steps. But if you solve everything here, you should get a moment of inertia of 25 kilogram meters squared. As always, I need to mention OpenStax online textbook. I got a lot of my practice problems today from there. So if you've gotten this far in the video, consider subscribing, and I hope this video helped. If you have any questions, put it down in the comment section.